class. In this lecture video, we're going to cover 5 example problems involving algebraic limits. And as you see, the first one is already on the board. So let's just go ahead and get started with it. So in this problem, we are asked to find the limit as x approaches 4 of this quotient function x minus 4, x squared minus 5x plus 4. All right, so the first thing that we should do is actually verify that there is a problem when we try to plug in the value x. Because if this is continuous at x is equal to 4, we can simply evaluate it and come out with a number. But notice that when I plug in 4 into the denominator, 4 squared is 16, plus 4 is 20, and then negative 5 times 4 is minus 20. The denominator really is 0 when I plug in 4, so we have to use the replacement theorem. And by the way, even in the verification process, recall that when we plug in a value like 4 and we get 0, if it is a root of the expression, the polynomial expression, it is also a factor. So that gives us a clue at how to proceed. Namely, we need to factor out the quantity x minus 4 in the denominator. And with that being said, can you think of 2 numbers that would multiply to positive 4 and then add up to negative 5? X minus 4 and x minus 1 will work. All right, so here at this point, we could invoke the replacement theorem. And in work and in practice, you don't have to write RT above. I'm just citing that as our source as we move forward. That is, we can cancel the common factor of x minus 4, and as long as we replace it with a function that is identical except at the point of the limit itself, then it will return the same value. So now we look at what we have replaced it with, and notice that when I plug in 4, we don't divide by 0. That is, this function is continuous at 4. And don't be confused with the fact that the function overall isn't continuous. It's not continuous at 1, but we're not looking there. We're looking at 4. So it's okay to simply substitute in and simplify our work, and we get the limit is 1/3. All right, so example problem 2, very similar to the first one. Here we're looking at the limit as x approaches 3 of this quotient function. And just like before, what we always want to do is test to see if we can plug in 3 and get a well-defined number. Certainly 3 minus 3 in the numerator is 0, and 0 in the numerator is okay, but 3 squared is 9, and we would have 0 in the denominator. And even if the numerator is 0, 0 divided by 0 is undefined. So we have to do a factorization and use the replacement theorem again. So as mentioned before, this is an important case. This is a difference of squares. And when you see the difference of squares, that always factors as conjugate pairs. That is, we look at x plus or x minus the square root of that value there. So x plus 3 and x minus 3 is how x squared minus 9 factors. And lo and behold, we see a common expression that could be eliminated, and we pass through using the replacement theorem, and we're able to replace the original function with a simplified form of 1 divided by x plus 3. Now, even though this function is not defined at negative 3, that isn't the place we're approaching, so it's okay simply to substitute in, because this function is continuous at 3. And then by substitution, we get that the limit is 1/6. All right, so for problem 3 is our first new problem model. This time we have a square root function, and we cannot break apart the square root across the sum. So this won't be the same as the polynomial factorization problems that we saw earlier. But still, just like in the first 2 problems, we first want to test by plugging in the value 0, and clearly if I substitute in 0 into the denominator, division by 0 undefined. So we have to figure out some type of trick in order to break things apart. Now there's a standard way to do this when it involves the difference or a sum in which one of the 2 terms is a square root. The trick is we're going to multiply and divide by the same expression so that effectively we're multiplying by 1. But what we're going to want to do is multiply by the conjugate. So the reason why I picked out problem 2 earlier is that a conjugate is the same two terms, but we change the middle sign. So we would multiply and divide by the square root of x plus 1 over the square root of x plus 1. And by the way, this is non-intuitive. This is a trick that will help you solve this version of the problem. So now we do the multiplication on the inside here. And the cool part about multiplying by conjugates is it's FOIL, right? So first times first. The square root multiplied by itself becomes the whole power, 1. But when we look at the inner and the outer, look, negative of this term plus positive of the term, the inner and outer cancel. So we only have to multiply first and last. Negative 1 times 1 is minus 1. Now below, I'm just going to leave it in an unexpanded form, just multiplying the x and holding on to that entire term in a parentheses there. Now with that being done, look what happens in the numerator. First, the 1 and the negative 1 cancel, and it reduces to x divided by x multiplied by the square root of x plus 1 plus 1. And you see, the reason why I didn't want to distribute this in is notice what happens here. This is factored out, so the x in the numerator cancels the x in the denominator, leaving us with the limit as x approaches 0 of this reciprocal function. 1 is left in the numerator, the square root of x plus 1 plus 1. Now, at this point, since we've done some algebra and some work on it, let's go ahead and verify that now we can plug in 0 and not divide by 0. Indeed, substitution of 0 into the variable slot x, we get 0 plus 1, which is 1. The square root of 1 is 1, and then 1 and 1 is 2. So the limit works out to be 1/2. And so, as I said at the start, this is a trick that we'll employ whenever we're looking at a square root function plus or minus a constant. We will want to multiply and divide by the conjugate, just changing the sign. So for instance, if the original was a plus, then the technique would be a minus. And by the way, that would give us a different value, most likely at the end, but I'm just illustrating in this moment the variation of that trick. We always multiply and divide by the conjugate. All right, so problem number 4. Again, we see a return of this form of a square root minus 4. And you might be tempted to try the same trick as we did in the previous problem. And the setup would be something like this, except this problem is different than the one before. Do you see what it is? Well, this time around, if I look at the limit point as x approaches 6, look at the denominator. Are we dividing by 0 when I plug in 6? We are not. And go back to the other 3 examples, that's been a common feature of every time we have to do an algebraic type trick. We assess the denominator and determine, are we really dividing by 0? But here in this problem, we're not. So actually, we could just directly plug in. And so be mindful of that. Not all limit problems involve factorization or some type of trick or technique. It's just to go ahead and first test out to see, do we divide by 0? If we do, you need to do something. If you don't, it just becomes substitution and go. So I plug in 6 here and there, and then we get 10 minus 6 minus 4 divided by 6 plus 6, which sums to 12. And then here on the inside, this would become the value 4. But the square root of 4 is 2, so the numerator is 2 minus 4, and the denominator is 12. So that this reduces slowly and steadily down to the value 1/6. All right, so on to our final example. Limit as x approaches 0 of the quotient function that you see on the board. All right, so hopefully after problem 4, you are on it, and we observe first that 0 cubed minus 0 squared, we really are divided by 0. So factorization or some other trick needs to be done. All right, so then moving on towards the replacement theorem, we see that in the denominator, we could factor out an x squared term. If I pull out an x squared term, what's left over here would be one copy of x, and what's left over here is just minus 1. And that's a match with the term in the numerator, so that we could cancel, apply the replacement theorem. But here, again, is something different than what we've seen in earlier examples. Canceling this factor here did not eliminate the problem. Notice that if I plug in 0 into x minus 1, that isn't 0. The problem piece was right here all along. If I plug in 0 into the factor that didn't get eliminated, that's still present. Okay, so what do we do in this situation? Well, here, if I divide by 1 over x squared, we have to know a little bit about the basic shape of reciprocal graphs. If I look at the basic form of 1 over x, it looks like this. It has two asymptotes. It runs up towards positive infinity as we go to 0, and it goes down to 0 as we shoot on out in the x direction. And over here, it's symmetric. These two copies look like mirror images of one another, and that's what 1 over x squared looks like. Now, the only difference is if I choose to take this quantity and I square it, then 1 squared is still 1, and we would have x squared. But notice what squaring something does to all negative numbers. If the value was minus 1 and we square it, we would get plus 1. So what effectively happens is this branch here, that's negative, that is when we look at 1 over x squared, swings around and comes up. There's a little bit more to it, because if I say square, if I look at the value 1/2 and I compare it to 1/2 squared, well, 1/2 times 1/2 is 1/4. So the y values get squashed a little bit more, but since it has this asymptotic shoot off to infinity in both directions, the essential feature of the graph is this. On both sides, as we approach 0, whether or not we are on the left or on the right, we are ascending to infinity. So this is not a does not exist situation. The output is unbounded, and that would be what we return in this limit problem. But in any case, that completes the 5 example problems that we'll see here and now. Hopefully you're having a good day. I'm sure I'll see you soon. Take care. Bye.